So now let's start with today's talk. We will have on the vector mathematics. I think this is just a revision of the things what already you know. And the force, velocity, displacement, all are the example of this vector mathematics. So what is this vector? How do we represent? Graphically, we generally represent as this tail and head arrow notation. And this, let's say this is a vector A, and we over on this later we used to write by a arrow. This is what the notation we generally we use in textbook. Also you will find in bold letter, you will find the vector is being denoted. So but here the writing in bold letter is difficult, so we will use this notation. Okay, and this is what vector, this is origin of vector, this is what head of vector, tail of vector, and head of vector. And unit vector, if you see the direction showing this, is generally represented as EA cap, and this is what this vector divided by its magnitude, or simply so this. So this is what this is known as unit vector. Its magnitude is 1, and it is actually giving, it is used to give the directional sense that in which direction it is acting. Now another thing, that if let's say we have also this unit vector, similarly we also have the zero vector. So and zero vector and zero are different. Okay, so this could also be vector. In order to understand that your origin is also 0 plus this in any Cartesian coordinate system, what we are representing, that is also a zero vector. That can be denoted as the zero vector. Position is at the 0, 0, 0. And we may have the force, all the component of force, if it is 0, then it is a zero vector. Though it does not have a great significance in magnitude wise, but it has its own importance, and that we will discuss later also. So this is what all this fundamental thing. Then we will have the equative vector. Let's say we have the two vectors A and vector B, and these two vectors will be equal only when the magnitude as well as direction should be equal. Magnitude and direction should be equal. If it is so, then we can say that the vector A and vector B are equal. So let's say the vector A we have, and if we are just making a parallel to this, having the same magnitude, if we are translating in parallel in anywhere, then this will also have the same, because it is equal vector, because it is satisfying the criteria of having the magnitude same, and as well as the direction of this vector is same. So a parallel translation of vector is not going to make any difference. Okay, then we have the vector addition. So these are all you have already studied. Just briefly I am explaining all. So if there are two vector that is vector B, let's say, and this vector A, and we have to find out the addition of these two vectors, as we are doing the scalar, that 2 plus 3, that is 5. But in case of vector, we cannot do simply A plus B, but it has its own way to do it. So what we will do, we will, let's say we have the vector B. On head of this, we will keep the tail of vector A. We will draw a parallel from here to here, and this, the joining, this is what B plus A. Also, this is the one way to do B plus A or A plus B. Now another way, that we have the vector A, and you are putting here vector B, and then this is, again you will get A plus B. So you here you can see that A vector A plus vector B is equal to vector B plus vector A. So this property is known as commutative property. Commutative property. Now this is very important. This is also known as triangle rule. Triangular rule. And any physical quantity, in order to satisfy that it is vector, it must follow this rule of addition. Then only we can say that it is a vector quantity. So any physical quantity, let's say here A plus B, both are representing the same physical quantity. Let's say the force, then it must be force. We cannot add force and displacement. We cannot add force and velocity. Rather, force plus force, vector A plus vector B. But it must satisfy this law, triangular rule. Then only we can say that it is a vector quantity. So I hope you all know this. Then there are some properties of the vector addition, that if there are three vectors, let's say consider vector A, vector B, vector C. First property what we have seen, that vector A plus vector B is equal to vector B plus vector A. This is known as commutative property. Commutative property. Then we can also do that A plus B. It all seems very trivial because already you have studied this. This is just a revision of all this. We can write B plus C, and this is associative property. So the vector addition satisfying these properties, then there must exist a zero vector, so that the A plus zero vector, vector A plus any vector, adding with the zero vector, it will give the vector itself. And further extension of this, if this is so, then there must exist minus a vector as well. Then we will have A plus negative of this vector is equal to 0. And see, though it appears very simple, but actually it is representing the natural phenomena, that if A exists, then minus A also exists. And so its whole relative word is dual, and that is also representing that plus and minus both exist together in order to make an equilibrium. And that's why I said that though zero vector for computation purpose, it has very less significance, but philosophically it is having very big significance. Even the symmetry and all, for all these we required this vector to define all these things. So existence of zero vector, existence of negative vector, we have studied. Then now if we will multiply the vector with a scalar, so multiplication of vector, multiplication of a vector with a scalar. So here let's say we have vector A, and if you are multiplying with some alpha, which is a scalar, here alpha is a scalar, and alpha is greater than 1, then what will happen? The direction, this scalar quantity is not changing direction. It's only increasing or decreasing the magnitude. If beta multiply with vector A, multiplying the vector A with beta, where beta is less than 1, so it is actually reducing the magnitude of the vector, but it is not changing the direction of the vector. So here also, if you see, if you have alpha, beta, and let's say beta times A, this will be equal to alpha beta. So this first it is with here beta A, vector multiply with vector A, and alpha, this is the bracket. So if this is true, then this is associative property, and we know that this is valid. So this, the scalar product of the, sorry, vector multiplying with of a vector with a scalar following this, the associative property. Similarly, if you have alpha plus beta and multiplying with this, then you can write this plus alpha beta, sorry, beta a bar, or if I have alpha summation of two vector, then I can write alpha a bar plus, sorry, alpha vector b. So these two property are distributive property. So we know all these things. Now, where we are going to use all these things? This seems very trivial, and how we are going to use this? So let's consider, I am further extending the discussion. Let's consider a vector, two vector, that is vector A, which is multiplied with C1, another vector, vector B, which is multiplied with C2. So this is what? This is a scalar multiplication, multiplying a vector with a scalar quantity, and then adding both. If it is 0, if this is 0 for C1 and C2 non-zero quantity, this is non-zero scalar, then we can say that vector A and vector B are linearly dependent. Why it is so? Because we can represent vector A in terms of vector B. So in order to define vector A or vector B, only independent thing that is either of A or B. So there is a linearly dependency between vector A and vector B. So if this condition is satisfying for C1 and C2 non-zero scalar quantity, and if the C1 A vector A plus C2 multiplication of vector B is 0, then it is saying that it is not linear dependent. If it is not so, so actually if this is so, so A and B are collinear, because it must be in either parallels or in a line. So it must be collinear. If it is not so, then what happened? C1 C2B is not 0, or 0 only when C1 and C2 both are 0. Then this is linearly independent vectors. I hope you have must studied all these things in linear algebra, or you have not studied, then you might study in your the further courses. And if there are three vector and which is satisfying the linear dependency, then that three vector will make a plane, and so on. So this is the scalar multiplication. When you're multiplying the vector, the importance of this studying is to know that whether it is linear dependent or not. Now, further moving the scalar product, of two vector. So if there are two vector A and vector B, angle is theta, and this scalar product, as you know that this is representing by the dot A dot B, this is AB cos theta, and where A and B are the magnitude of vector A and vector B respectively. Okay, if you are getting two vector are perpendicular to each other, if the two vector are perpendicular to each other, then you will have A dot B is equal to 0. If it is in one line, then it is simply AB, and so on. So here we can also have a relation that A dot product with B plus C, you will get, you can write this as A dot C. So this is what distributive law, it follows the distributive law. Now, if we move to the vector product, of two vector, again we are having two vectors, that is, one is B or A. So here this A cross B, it is denoted by the vector product is by the term cross, and this is what the vector product, and its magnitude is defined as AB sine theta. Okay, so this angle, let's say theta, so AB sine theta, but its direction, this is what magnitude. Okay, this is magnitude, and the direction is defined by using the right hand thumbs rule. Right hand thumb rule. So here if see, if we are doing A plus A cross B, then we have to, we here at vector A and moving in direction of the B by using our right hand, then you will find that the direction of this vector A cross B is inside the board. Okay, if we are having vector A here and this is vector B, then you will have this A cross B that is outside the board. Okay, so towards us. So if you see here the B cross A, this is B cross A and A cross B are not equal. Are not equal, or actually it is A cross B is equal to minus B cross A. Where we have used this concept, torque is one of the example, or moment is one of the example of vector product of two vector, where we are having the position vector R, we are having some force vector F, and we are defining the torque or the moment as R cross F. So this is one of the example what already we have done this during our mechanics course. Then some law, if you see that the vector product is satisfying certain law, and this is, let's say, if this is so, then this can be written as plus A cross C. So this is what distributive law. Distributive law or rule. Then another very important thing, and I must ask you to prove this, try to understand whether it is correct or not. This cannot be equal to, so here associative law is not valid. Okay, if you see A cross B cross C, where B cross C is in bracket, it cannot be equal to bracket A cross B cross C. So we cannot do this. So here associative property is not valid. Not valid. So this is what the vector, a scalar product of two vector, that is we are using with the dot product, and the work or energy we are using F dot D, we have used during our mechanics course. The vector product of two vectors, that is the cross product of two vector, this is a vector quantity. So finally you will get a vector quantity. Cross product of two vector will give you the vector quantity, and the dot product of two vectors will give you a scalar quantity. So we have to be careful that one, that's why it is known as the scalar product of two vectors, and This is known as the vector product of two vector. Now similarly, we have the scalar product of three vector. If you see the triple product of vector, triple products of vector. So let's consider we are having the vector A, we are having vector B and vector C. So how many combination we can have? We can have one combination as simply vector A multiply with B dot C. So if you see, this is what, this is a scalar quantity, and this scalar quantity multiply with a vector, and this is just neither dot product not the cross product. This combination also we can have. So another is, we can have your well known triple product, that is scalar triple product, and this this is what known as scalar triple product, and this is a vector quantity, this is a vector quantity. So dot product of two vector quantity, finally you will get a scalar quantity, and this is volume of parallelepiped made by the vector A, B and C. So this is a scalar quantity. Okay. Now third, this the vector product, vector triple product, and this is a vector quantity, this is a vector quantity. So finally you will get a vector quantity. Okay. And this is the reason this is known as vector triple product. Vector triple product. Now let's have a little more discussion on a scalar triple product. And this is A, vector A dot vector B cross vector C. This is also represented as the bracket A, B, C. So if let's say you are having vector A here, a permutation we are considering, a cyclic permutation, and if you are following the cyclic permutation in anti-clockwise, so it means that either A, B, C, or this will be equal to B, C, A, or it is equal to C, A, B. So if you are changing this order of the vector but following the anti-clockwise rotation, then the sign will not get changed. It will have will give the same thing. So it is B dot C cross A. Here it is C dot A cross B. Okay. If it is opposite of this, so if you are having the cyclic permutation and the order is in clockwise direction, then you will have ABC is equal to, if I say A, B, C is equal to minus B, A, C. So these are some property of this scalar triple product, and also you know that this is the volume of the parallelepiped made by the three vector A, B and C. Okay. Now let's see that what is the scalar triple product, vector triple product. I'm going a little fast, considering that you already know all these things. Scalar triple product. So here we are having A cross B cross C. Now, what is the physical? How do we understand it? Geometrically, how do we represent it? So let's consider this is a vector B. This is a vector C, and this is a vector A. Now, first let's think about this. This is B cross C. So B cross C means what? A vector which is perpendicular to both vector B as well as vector C. So this should be, let's say, this. So this is a vector which is perpendicular to both vector B as well as vector C. Okay. So it is actually the perpendicular to the plane made by vector B and vector C. So this is the plane made by the vector B and C, and this vector should be perpendicular to this plane. Now we have to multiply the cross multiply with this vector. Now if you see that when you will do the cross product of vector A and vector B and the cross product of vector B and C, then you will get a vector that will lie into the plane of vector B and C, but at the same time it must be perpendicular to vector A as well. So final product should be, it should be the it should lies in the plane formed by cross product of two vector and must be perpendicular to vector A. So, and also you know this relation between, this can be written as A dot C B minus A dot B C. So what is this? Here, this is the relation, and also even in 12th standard you have derived this relation. You know very well this relation. So, but if you see this relation, then from this you can understand. Can I write this as A cross vector B cross vector C as C1 B plus C2 vector C? So this, since this vector lies, this vector A cross B cross C vector lies in the plane of B and C, so that's why we can write as a some linear combination of vector B and C. Okay, this is the reason, and this is what we have proved also during our undergraduate courses. So this is all about the story about what is the vector, and very briefly I have described the vector addition, the significance of zero vector, unit vector, vector product of the two vectors, then scalar product of two vector, scalar triple product, and vector triple product. So these concepts, you already know all these concepts. So we have revised all this concept. Now I would like to have some question, and then we will have a small break. Okay, so please ask one by one. You can ask a question to me. Yeah, do you have any question? No question.
Yes, sir.
Yeah.
I have a question. In physically visualizing these two things, like this scalar triple product and vector triple product,
So
like this A dot B cross C is a volume.
yes, it is a volume.
Yeah, and this A cross B cross C is also will also be a volume.
No, this is not volume.
So what will be the physical interpretation of this A cross B cross C?
Yeah, that I have just explained you.
That is a vector.
Yeah, let me explain it again. So we have the vector A cross B cross C. Fine.
Yes.
Now let's see, let's consider this is vector B, this is vector C. Okay. Now
Yes. Sir.
first we have to find out what is this B cross C. Okay. Now this B cross C, it should be when you will rotate your right hand from B, vector B, towards vector C. Okay.
Yes.
So the perpendicular to the plane made by vector B and C will be, if this is the plane, for example, let's say I drawn as a plane, and perpendicular to this is what? Vector B
B
cross.
cross C. Yeah.
Okay, and it must be perpendicular to both vector C and vector B as well. Okay, now if this is vector A, okay, now we have to find vector A cross vector B cross C. So now we have this vector B cross C. We have to multiply the vector A with vector cross product of vector B and C. So what we have to do? We have to take our right hand. We have to rotate the from vector B towards vector B cross C. And then when you will do this, you will find the vector product of these three vectors will be perpendicular to vector A as well as vector the cross product of vector B and C. So finally, it will lies in the plane of the vector in the plane formed by the vector B and C. Okay, it is not necessary it will along B or along C. That finally you will
Yeah.
get magnitude. Depending on the magnitude, you will have some value assigned to this also, but it will lies in the plane formed by vector B and vector C. Okay, so
Ye-
this is what physical or geometrical interpretation of this quantity. Okay,
uh,
whereas, is it clear?
yes, sir. It is clear. Yeah.
That's why we have written this as some C1B plus C2C, and that their C1 is equal to A dot C, because it's a well established relationship, and minus A dot B. So this is what? This is because this vector lies in this plane formed by the vector B and C. That's why we can write this, and that is the reason we got this expression. Okay, so this is the physical interpretation or geometrical interpretation of triple product of three vectors. Similarly, if you see the scalar product of three vector, so that is this. So let's consider we have vector B, we have vector C, and this is what perpendicular, it is P cross C. Here you have some vector A. So, and you have to find out the dot product of this, isn't it? So this is vector, this is vector. Finally, dot product, you will get a scalar quantity, and this scalar quantity actually is equal to the volume of parallelopiped made by the vector, the volume of parallelopiped formed by vector, formed by vectors A, B, and so this is what the physical interpretation of the scalar product and the vector product of vector triple product. Okay, is it clear?
Yes, sir.
Okay. Now, one another important thing I would like to also tell you, that plane is also, the plane area is also a vector. It is also a vector quantity. So I have discussed that. Let's consider a vector A and vector B, and when you are making a cross B, then you will have a vector which is the perpendicular to the plane formed by vector A and vector B. isn't it? So actually, it is representing it's if I find out what is the direction of along this, let's say E, so this E will be here. Sorry, this cross one. So any plane we can determine the normal direction to the given plane, we can determine by using this if there are two vectors. Or in general, if there is any plane, let's say the plane is S, and if we are using the right hand thumb rule, if we are just making a contour and with a travel sense, then this normal to this will give you a normal direction, and the vector can be written as S, the plane vector can be written as S and M. So we are using this in for solving, like when we are determining the stress or we are determining the traction force at any given surface, then we are using the plane area as well. And in many cases we are using electromagnetic force, and also we are using the plane area concept. Okay, so this is what briefly I have revised the concept of the vector, mostly the vector algebra, not calculus. Right now, I will go for in those portion also. Not now, but I will discuss these things also.